On to section 5. I actually did not skip section 4. I just did not label it on the earlier slides, but we are now jumping to section 5, and it's about uncertainty in measurements. This will have to do with significant figures. All measuring devices, that would be balances, pipettes, thermometers, are made to limited specifications, and we use our imperfect senses and skills to read them. In other words, there are going to be errors or uncertainty in any measurements that we take. Every measurement includes some uncertainty. The device we choose depends on how much uncertainty is acceptable. For instance, using a supermarket scale that measures in 0.1 kilogram increments is acceptable. When you weigh potatoes with a scale, it may read 2.0 plus or minus 0.1 kilogram, and that's okay. The plus or minus 0.1 kilogram expresses the uncertainty, and so we are giving it the benefit of the doubt that it could be in the range of 1.9 to 2.1 kilograms. And that's what it's saying here. In the lab, a chemist uses a balance that measures in 0.001 kilogram increments. Definitely different from a supermarket scale where it's going to be in 0.01 increment. So what we're saying here is that a chemist will use a more sensitive balance compared to a supermarket scale. Using this balance, a chemist may weigh a substance at 2.038 plus or minus 0.001 kilogram. So the substance weighs between 2.035 and 2.037 kilograms. So see how the range is going to be in the thousandth scale. It's still going to be 2 if we were to round it to the nearest whole number. However, because a chemist uses a more sensitive balance, that means that we're actually keeping track all the way to 1 out of 1,000th of a kilogram. The greater number of digits in the measurement using the lab balance means we know the mass of a substance with more certainty than we know the mass of potatoes, which we really don't care. We're not going to care if the mass of the potato is off by 1 out of 1,000th. But in a chemistry lab, those values do matter. We always estimate the rightmost digit of a measurement using the sign plus or minus. However, we usually drop the sign and assume an uncertainty of 1 unit in the rightmost digit, and we will show that what that all means in just a little bit. The digits we record, both the certain and the uncertain ones, are called significant figures. The greater the number of significant figures, the greater the certainty of a measurement. When it comes to measurements and significant figures, as well as certainty, it really does matter what type of equipment or measuring device we're using. So in this slide, we see 2 different thermometers. We have thermometer A and thermometer B. And when we look at the numbers, we can see that it goes 1 mark over. So we have 20, 21, 22, and then the same thing for thermometer B. The difference is that for thermometer B, we are given more gradation lines. So we see more of these tick marks right here that will help us to be more certain of our measurements. So let's go ahead and write the measurements considering the correct number of significant figures. So the first thing you have to consider is to write the number that you are absolutely certain of. And in this case, for thermometer A, we are absolutely sure that the line, so this red mark right here, absolutely crossed 21. So we're going to write 21 for sure. And then we get into this zone where we're going to have to guesstimate. And so looking at this, I would say it's close to maybe an 8. Again, we're just looking at thermometer A. And normally, I don't know if you remember from physical science when we did this, I will ask you to underline the uncertain number. You don't have to for this class, but this underline mark signifies that this 0.8 right here is an uncertain value. It's something that we had to guess to the best of our abilities. And so in this case, this is going to be 21.8 degrees Celsius using thermometer A. Now for thermometer B, let me just draw a line here to help me. Okay, that's not a straight line. Let's see. Well, okay, I think it's more in the middle right there. So if we use thermometer B again, in terms of significant figures, we're going to go ahead and write the certain numbers first, and we are certain that the red mark crossed 21. So we're going to do that. So 21 point. And then I also know for sure that it definitely crossed the 0.5 line right here. So 0.5, we're not going to write that here, but we know for sure it crossed 0.5, 0.6. Now for 0.7, and let me just take away that line. It's not really straight. Okay. So we have, okay, 0.5, 0.6, and I would say it's probably somewhere in the middle. So I know for sure it crossed the 0.6 mark. And then now we have our guesstimated value, which is the halfway point, so 0.005. Okay, so in this case, the 0.00 or 0.05 here is the uncertain value. And so that's the one that we're going to underline. And again, this is in degrees Celsius. So using thermometer B, our measurement will be 21.65. So comparing the two, we will see that thermometer B, and again, this is without reviewing the rules for significant figures, we can see that using thermometer B with more of the tick marks or the gradation lines, we will have more digits. And more digits mean that that measurement has more certainty. Now we're going to practice taking measurements. And again, the rule is that you list the number that you are for sure of, and then you add one estimated value. And a lot of times, the practice is you underline that uncertain value. So we're going to start with volumes with our first graduated cylinder. Okay, I'm going to just go ahead and draw a line for where the meniscus is so that it's clear for us where our measurement is. So we have from 50 to 100, so it looks like each line jumps by 10. And so I know for sure we cross 50, and then we go on to 60, 70, 80. So I know for sure the 8 mark has been crossed. But now we have this line between the 80 and the 90. And I'm going to say it's about 88. So see how the last value, so this last 8 right here is our best or my best estimate. And so that's our uncertain value, and then that is usually underlined. And of course we have our unit in ml. Okay, now let's say we add more gradation marks. So we have our second graduated cylinder, and it looks like it goes from 10 to 20, and there are 10 lines in between. So those lines go by 1. And so our meniscus is right here. I know for sure, I can see for sure it crossed 40, and then it goes 41, 42, 43. Okay, 44 I would say is the last certain value that I can see. So then we're going to go ahead and estimate that last value, and from my standpoint, the line is between 4 and 5. So then I'm just going to go ahead and call it 0.5. So this last value, again, is our estimated value. And so it is underlined, and we have 44.5 ml. Our third graduated cylinder, okay, our line is right there, and it jumps from 1 to 2 with 10 markings in between. So that tells me each mark goes by 0.1. And so the liquid goes to, we know for sure it crossed 3. And then we have 3.1, 3.2, 0.3, 0.4, 0.5, 0.6. That is my last for sure number. So 3.6. And again, the meniscus looks like it's between 0.6 and 0.7. So I'm just going to call it a 0.05. So our value is 3.65. Again, that 5 is the estimated value. And this is in ml. As you can see, the more gradations we have for our measuring device, the more numbers we can have after the decimal point. And so that makes that measuring device more precise because we're guessing less numbers. Okay, we're moving on to measuring length. And here our first one, we have not even a marking, we just have, it just says 100 centimeters. So actually in this case, even that first value is an estimated value. So if I were to say this is the midway point, in my standpoint, I'm going to go ahead and estimate this to be 40 centimeters. And this value right here is the estimated value. So this number is very estimated. Depending on who's measuring it, it could vary. All right, let's say we add more markings. So now we have every 10. So we have 10, 20 centimeters. And our line is right here. So I know for sure it crossed 50. And this marking is between 50 and 60. So that 5 is for sure. But then this value in between 50 and 60 will be estimated, and I'm just going to go ahead and say it's going to be a 5. So that 5 is an estimated value. Again, what that means is that if somebody else were to measure this number, the first one that we are certain of, more than likely it's going to be the same as the other person's measurement. Now this estimated value, that's the one that's going to vary depending on who's measuring it. Now there are numbers that are closer to the true value than others. Again, depending on who's measuring it. Lastly, we have this ruler, and we have more markings, which is better. All right, so it looks like the line ends right there. I know for sure we crossed 30, and each line is going to be by 1, and that's the last line before 40, so it's going to be 39. So I know for sure the values 3 and 9, but then we can estimate one more, and in my standpoint, I do feel like it's right on 39, so we can put a 0. Again, this is an estimated point. Another person might say 39.1. But the point is that the 3 is certain. So if somebody else is measuring it, they will write a 3. And then 9 is for certain. So more than likely, they're probably going to put a 9. It's going to be this value right here that's going to vary depending on who's measuring it. So again, that is in centimeters. So the point of this exercise is to show you that the measuring device does matter if you want to be able to predict or to get a more precise measurement. More precise meaning every time you measure it, you're going to come up with values that are close to each other. Now, if you have a measuring device that is like this, where you don't have a whole lot of gradations or you don't have a whole lot of marking, then every time, or if somebody else measure it, your measurements will vary. So the measuring device does matter. We're going to get into reviewing the rules for counting significant figures or significant digits. But before we start, let's go ahead and label the zeros. First, we have what we call leading zeros, and leading zeros is when we have 0.0 whatever that is. So it could be 0.00 or 0.0000, but the point is that it leads the decimal number. Next, we have zeros that are in between, and they are in between non-zero digits. So in this case, this 0 right here is between 5 and 8. So those are zeros in between. And then trailing zeros, as the name implies, are zeros that trail after. So they are the zeros that will be after a non-zero digit if there's nothing else. So it could be 1 0 here or several zeros after. So the first rule is that non-zero digits are always going to be significant. So we count them as a significant value or a significant digit. Next, in between zeros are also significant. So in this case, the 0 here will be considered a significant digit. So we already have non-zero digits as 5, 8, and 3. So counting, we already have 1, 2, 3 significant values. And then we have 0 in between will be significant. So already we have 1, 2, 3, 4. Leading zeros are called placeholders and are not significant. And so our leading zeros right here, we do not count them as a significant value or significant values because they are considered placeholders. And what that means is that if we turn this number into scientific notation, those leading zeros will essentially disappear. Now, trailing zeros can be tricky. They will be significant if there is a decimal point in the number. So in this case, there's a decimal point right here. So this trailing zero will be considered significant. Now, it is not going to be significant if there is no decimal point in the number. So far, following the rules, we have 1, 2, 3, because they are non-zero digits. And then the fourth significant digit is the 0 in between. And then the fifth significant digit is this trailing 0 because there's a decimal point in the number. Again, the leading zeros we do not count because they are placeholders. So overall, this number right here will have 1, 2, 3, 4, 5 significant digits or significant figures. The next rule is that we will not take into account numbers of significant figures for exact numbers. For example, the exact known numbers, such as an hour is equal to 60 minutes. We don't count the significant digits for 1 hour and 60 minutes. Or counted numbers such as counting exactly 3 coins. If the problem says there are 4 coins or 4 circles, we do not count that value when we are talking about significant figures. All right, practice with significant figures. And we have our first value at 10.500. Okay, again, all the non-zeros are going to be significant. So we have 1 and a 5. And then in between zeros will count. So the 0 will count. And then zeros after the decimal point will also count. So in this case, we have 5 significant figures. Okay, all of these are non-zeros, so all of them will count. So that is 3. Okay, we have leading zeros. And again, leading zeros are not significant because they are placeholders. What that means is that if we turn this into scientific notation, they will disappear. So this value would be 6 times 10 to the minus third. And then here, because we got rid of those leading zeros, we can see that we only have 2 significant figures. When we have scientific notation, we don't really count this. So in this case, we have 3.03. We have an in-between 0 that will count. So this has 3 significant figures. Okay, we have 1,000 megameter. And what this is telling us is that it seems to be more of an estimated value. So the significant figure is just going to be this one right here. Now we have 100 and a dot. So what that means is that this measurement is exactly to the 100. It's not rounded to 100, unlike this value, which because there's no decimal point, it's rounded to 1,000. Number 6 says it is exactly 100. So that means these zeros will count. So think of it as these zeros are in between the 1 and the decimal point. So they will count. Also, there's a decimal point there, and according to our rule, those zeros will count. So this has 3 significant figures. Next, we have 20.000, and again, this zero will count, and zeros after the decimal point also count. So this has 5 significant figures.